Okay, this lecture is parameterization of surfaces. And so let's draw a arbitrary surface here. Say it looks something like this. Now surfaces are necessarily in space. Okay, and unlike lines or curves which are one-dimensional, surfaces are necessarily two-dimensional. And we can see that if we just pick an arbitrary point, let's say here, or a particular point, and we'll call that x naught, y naught, z naught, and an arbitrary point, which could be anywhere, we'll call that x comma y comma z. To get from this point to this point, we have to go in at least two directions. So the idea is, if you say start here and draw some lines, say grid lines, let's say they look like that. Well, that gets you along that direction, but we now need a second direction. So say we have grid lines that look like that. So now you can see that to get from here to here, it's so many of one of those grid lines and then so many of the other. And that's why we call it two-dimensional. And it's because of this property that we can take any surface, even if it lives, well, it has to live in three-dimensional space, we can map this surface onto a two-dimensional plane. So we have x, y, and z here, and let's pick our parameters to be s and t, for example. So parameterization just means let's come up with the equations that map these points into this plane. So this plane might be something like that. So this point here might map to this point, and this point here might map to this one, and so forth. Okay, so we're going from 3 variables to 2 variables, and we call these variables parameters. All right, let's take some examples. We'll start with graphs first. And graphs are very easy to do. By a graph, I simply mean we could write the surface as a function of x and y. Okay, so we want to create parameters, say s and t, and the appropriate equations that do that mapping. Well, we can very simply just say, let's let x equal to s, and y equal to t, and z. Well, if we know x and y, we know s and t, so z has to be f of s and t. So we've gone from 3 variables to a world of 2 variables, and we're done. As long as we specify how s and t range, provide the boundaries for s and t, or it could be minus infinity to infinity. Now, so this, along with those boundaries, are that parameterization. Now, we often write this situation in vector form. So the vector r, the position vector r, is by definition x, y, z. And you can easily see that that's simply s, t, and f of s, t. And again, with the appropriate bounds, we're done. Now, often, instead of using s and t, we can use x for the x variable and y for the y variable. And then for z, we can just write it as f of x, y. Okay? So there's really no need to create two new parameters. We can just name them x and y instead of s and t. So we'd have here x, comma, y, comma, f of x, comma, y. All right. The next example is a plane. Well, a plane, we've already learned that planes are of the form ax plus by plus cz is equal to d. So they're, by definition linear, which means we can write z equals and just solve for z. So planes are, by definition, graphs. So all we have to do is use the same technique. So I won't bother to even do that. Let's move on to cylinders. And let's take a cylinder. Let's take a simple cylinder. Let's say it's centered about the z-axis. Okay, and let's say it starts at, we'll just pick an example here. We'll let the z go from 0 to some number here. We'll make it 10. Okay? And cylinder is going to have a radius. So let's let that radius be, well, we can make it r. Okay, so how would we parameterize the surface of that cylinder? Well, here's how it goes. Let's think about this circle here in the xy plane. So in the xy plane, the circle of radius r, it looks like that, and we know how to parameterize that. It's simply going to be x is r cosine, I'll write theta instead of s, why not? And then y is r sine theta, okay? Now r is a constant, it's just a number, because we're looking at a particular cylinder here, not a general cylinder. So these are just constants. So here's the variable similar to s, but what is z? Well, z is just a number that indicates the height associated with that surface. So z is just z. Or if you like, you call it t. Doesn't matter. Okay. Well, let's actually do that. Okay. So here's 3 variables, and here's your parameterization. Instead of s comma t, it's theta comma t. And all we have to do is provide the bounds. Well, the bounds, here's theta. It's going to be 0 to 2 pi. So theta is 0 to 2 pi. And t is the same as z. And in this particular example, z goes from 0 to 10. Okay, I'm sorry. Oh, no, that's right. It's r cosine and r sine, and r is just a particular number. Yeah, I thought I wrote 1 here, but I didn't. All right, so that's a cylinder. You can think of a cylinder as maybe it's made out of paper, and if you just cut it, vertically and unwrap it, stretch it out and put it over here somehow, and here's, say, theta, which goes from 0 to 2 pi, and the other guy is t, and that goes from 0 to 10. So you just take this thing that you cut and stretch, or not stretch, but put down on the plane, and the region looks like this. So this point here would be theta 0, z, or t0. So this point here maps to this point, and so forth. Okay, so that's how it works. And these theta things are the theta grid lines, and the z values are the t grid lines. All right, next is a sphere. A sphere, and we'll keep it simple. We'll make it a sphere of radius, I don't know, a, centered at the origin. So this radius value here is a. You know, it's x, y, z. So we're in space, but the surface is just two-dimensional. Okay, so how do you describe it? Well, it's very much like change of variable to spherical coordinate systems. Okay, the trick is, though, we want to only use two parameters. If you recall, spherical had a rho, a phi, and a theta. We're going to do something very similar. If you remember, in spherical, x was rho sine phi cosine theta, y was rho sine phi sine theta, and z was rho cosine phi. Okay? X, Y, Z, spherical change of variable involves rho, phi, and theta. Well, too many. But good news, it's just a particular sphere. This sphere has a rho of exactly A. So we can replace rho, the variable rho, with the number A. So now we have it. The parameters are phi and theta instead of s and t. Doesn't matter what we name them. So all we need are the bounds. So phi, that's that angle from the North Pole, if you will. Well, that goes from 0 all the way to the South Pole. So that's 0 to pi radians. And theta, well, once you're at a point here, now you have to go around the world. So theta goes from 0 to 2 pi. So in a picture, S and T are really phi and theta. And phi again goes from 0 to pi. And theta goes from 0 to 2 pi. So it's rectangular. So somehow you kind of cut the sphere and you nail down the corners and you do some kind of stretching to make the whole thing work. And that stretching is dictated by these three equations. So it's the same idea. You have phi and theta for your parameters. Phi is like a latitude, if this was, say, planet Earth. And theta is like a longitude. Okay, that's all there is to it. Now, why is this important? Why do we parameterize at all? For curves in space, we parameterize to calculate line integrals. For surfaces, we parameterize with two variables to calculate surface integrals. And that's something we'll cover shortly. Thank you.